My talk is going to be modeling and analysis of multi-timescale uncertainty in energy system planning. Um, uh, well, uh, First of all, I would like to say a bit more about myself, but of course, thanks for Felipe's introduction. So my main research interests are, stochastic programming, energy system optimization, and some algorithm development for optimization problems. And recently, I focus a lot on machine learning and quantum computing enhanced solution algorithms for stochastic optimization problems. And yes, like Felipe mentioned, I did my PhD at NTNU, and before that, I did my master in Edinburgh, and I also got a degree in math from Hua University. Yeah, so before I joined the University of Southampton, I was a researcher. Well, in a short period of time after my PhD at NTNU, and in addition to these academic appointments, I was visiting some universities in Europe and the US. And if you want to know more about my research and stuff, you can check my website for more information. Okay, so today's talk is going to be largely based on these two papers. The first one was recently published in April this year, and the second one is a manuscript that is available on archive. Right. So, um, first of all, I would like to give you some background regarding the energy trend in Europe. Well, as you may know, the EU has a very ambitious climate target, and the European Commission aims to have 300 gigawatt offshore wind power in the North Sea by 2050. And in addition to this renewable power, the other energy carriers, such as hydrogen, is also given a very important role in this energy transition. Um, and so on top of this, in addition to this, new investment and targets towards this renewable power and renewable energy, we also have a very mature existing energy infrastructure, mainly natural gas, that may be retrofitted for future hydrogen systems. So that is, a big picture of the European energy trend towards renewables and towards renewable power and renewable energy sources. Like I said, the climate targets in Europe are quite let's say ambitious. And if we take a look at this plot to the left, you can see that basically we need to in all sectors the emissions needs to reduce to near zero by 2050. And in addition to that, we also need some excuse me. We also need some carbon removal technologies, CCS technologies. And when we talk about energy in Europe, we cannot omit Norway, because Norway is a very big player in providing energy in Europe. And from the region perspective, it also targets to reduce its emissions by quite a lot by 2030. So yeah, so basically this emission reductions needs to take place in the entire European continent. And so, like I mentioned in the first slide, the EU has aims to make investments in 300 gigawatt offshore wind. but also in some other policy packages like this Fit for 55. It aims to have a 430 gigawatt wind, not only offshore but also onshore by 2030. And again, on the hydrogen side, we have a lot of policies, Fit for 55, Repower EU, that aims to really boost the production of green hydrogen. Um, but the fact is that the global renewable energy, hydrogen production in 2020 was below 0.5 megaton, which is far below what the EU, aims to achieve by 2030. And we are not that far from 2030, if you think about it. And in terms of the existing energy infrastructure, well, as you can see in this plot to the left, is this plot illustrates all the gas pipelines from the Norwegian continental shelf to the rest of Europe. And and of course, if you look at the European continent and the UK, you will find also, very mature onshore gas system. And these networks these networks for natural gas can be potentially used for, hydrogen. So what we want to analyze here is, under what condition some of the infrastructures can be retrofitted for renewable energy production and transportation. And of course, if you look at this Norwegian continental shelf, you will find the offshore oil and gas platforms. And an idea is to retrofit these oil and gas platforms to produce hydrogen offshore and transport hydrogen to the to the demand side. But all these new investments, retrofit, and also there is another type of decision that we need to analyze, which is the abandonment of existing energy infrastructure, because you can either abandon your platform or retrofit to something new, something different, or you can keep this platform producing oil and gas. So we need a model to analyze the economic trade-off, and that is what we aim to do in this in the proposed REORIENT model. Because, in a lot of studies, they either only consider, retrofitting or abandonment or new investment, but they never, it's rarely, seen a model that that integrates all these aspects. So I think now it's not hard to find that we are targeting a long-term planning problem, and we want to meet certain emission targets. And if you think about it, for these types of problem, we are facing uncertainty from two different time horizons. One is the short term, where you make your operational decisions, let's say system operation, and also you face uncertainty in the long term, which can be this policy uncertainty, let's say the CO2 limits, or let's say the hydrogen policy, for example. So that, well, for us, we would like to capture these uncertainty from two different time scales, and here I just give you some examples what do I mean by this multi-timescale uncertainty. So in the plot to the left is an example of the the wind and solar production and the energy, the power load in Eastern, Northwestern European countries without Norway. And then this is for scenario one. And then if we look at the same period, but from a different scenario, you can see wind and solar generation and load pattern is significantly different. This is scenario two. And if we move to scenario three, you can see again, it's very different. And I think the key here is to is to capture this uncertainty when you make your planning, when you examine your investment decisions on your operational problem. And on the other hand, like I said, we have uncertainty that reveals in the longer term, which is this one example is this oil and gas price uncertainty. Here is actually, this is one of the scenario tree we use in our case study. And as you can see, the uncertainty reviews every 5 years. Yeah, so we need to capture both excuse me. We need to capture the uncertainty from both time horizons. And I think fairly efficiently, because as you can, it's not hard to find that the model will, can easily explode, in size if you want to capture the uncertainty from these two time horizons. So that's why we dig into the literature and see what kind of the modeling approach we can use to model the multi-timescale uncertainty efficiently. And eventually we find this multi-horizon stochastic programming, which I will explain what it is in the next slide. But this multi-horizon stochastic programming was initially proposed in 2014. But then by looking into the literature, we noticed that this MHSP is just a type of multi-stage stochastic programs with block separable recourse, which was proposed in a paper back in 1986. And then there are some theoretical work along this line. And from our side, we mainly focus on exploit the problem structure of MHSP and develop efficient solution algorithms to solve large-scale problems. And so for today, like I said, some part of the talk will be based on the last paper presented here. Okay, so with all this background and the literature, our research questions are, fairly clear. First, what is the impact of the multi-timescale uncertainty on energy system planning? And also, what is the value of existing energy infrastructure in the energy transition? And of course, how we can solve this large-scale model efficiently. And the motivation is also clear now. Again, we would like to use this multi-horizon stochastic program to model the uncertainty, and we will develop solution algorithms and utilize parallel computing to solve the underlying model efficiently, and we will analyze the impact of multi-timescale uncertainty. So because if we go back to the literature in the past, mainly from our side, we did a lot of work along the line of solution algorithms for MHSP, and the key of MHSP is to efficiently capture multi-timescale uncertainty. But there is no paper actually systematically analyze the impact of this multi-timescale uncertainty, and that's why in this talk, in this paper, we will try to um, try to fill this gap. Okay, so what is MHSP, Multi-Horizon Stochastic Program? So an example of this MHSP tree is presented here. So basically, the blue circles here are the points in time you make investment decisions. And also the blue part of the tree is where your investment, well, long-term parameter or certain parameter reviews, okay? And the red squares are the point in time where you make your operational decisions. Let's say you make operational planning every hour or every half hour. You know, you have different time resolution. And for the blue circles, the time resolution here is, you know, it can be every year or every 5 year. So you can see these include includes the uncertainty from both short-term and long-term time horizon. So there are different ways of formulating this problem, and one of the formulation is this node formulation. Um, so basically, you denote all these investment and the blue circles as investment nodes, and you denote the. So basically, the each block of the red squares are also your. You can also denote them as a node which includes all the operational periods in that node. And so if we look at these equations here, um, equation one is the full master problem where, you know, f of x calculates the investment planning costs, and x are your, you know, investment related variables. And calligraphic X is the you know, the feasible region for X, and then you have different subproblems G of XICI, which are basically the blocks of red squares, and then G of XICI takes in two parameters, two vectors of parameters, xi, which is the right hand side vector, and ci, which is the cost coefficient. So, and then g of xici is linear programming. So if you are familiar with Bender's decomposition, we can decompose this problem in a two-stage Bender's manner, where you put all the blue parts in your reduced master problem, and then each block of red squares are your subproblems. And then it's natural to see that the each block of the well, the blocks of subproblems can be solved in parallel. So this is a geometric illustration of this Bender's decomposition. But again, this is how you formulate the reduced master problem, where you only keep the blue parts, and then you still keep all the constraints related to the investment. And then for the operational part, you replace g of xici with an auxiliary variable beta I, and then you build cutting planes to approximate g xici. And then in this illustration here, you can see, well, like again, the red square here includes all the operational periods in that node. Okay. And then as you can see, we use dashed line to represent the fact that we don't know g of xc in this case. Instead, we build cutting planes to approximate these dashed lines. And in this case, you know, the red dots are the points we evaluate our subproblems on, and then in this case. As you can see in this illustration, we have three cuts built for each subproblem. because we performed 3 iterations, as you can see in these equations in the bottom right. And it can also, well, some people also refer this as multi-cut Bender's decomposition, because every iteration you build multiple cuts. In this case, you build one cut per node. Okay. So well, I think this is the basic idea of the Bender's decomposition and how this cut there's some geometric illustration. For the sake of time, I will not really go into the details of the pseudocode and stuff. Well, but if you look at the title here, okay, so parallel stabilized Bender's decomposition. So now we understand the Bender's decomposition part, but again, for the problem that we are trying to solve later, purely Bender's decomposition is not working well. We need some other tricks, and one of the trick is to use parallel computing to parallelize the solution of the subproblems. And another trick is to stabilize the Bender's decomposition. And in the next 2 slides, I will explain what we do there. So in terms of parallelization, what we did in this paper is that we use a synchronous parallelization to solve the subproblems. Okay, so what do I mean by that? I mean, what I mean is, once the reduced master problem propose a solution vector, well, the investment decisions X, we then fix them into the different subproblems, and then in this case, we fixed. Well, of course, we fixed to all the subproblems, but then we will send the subproblems equally across the threads we have. And in this case, we have 4 threads, and then we solve SP 2, 4, 2, 1, 4, 3 first in these 4 threads, and then well, they probably will have different solution time, and then once this thread is free, we will solve the next subproblem, and so on and so forth, and then we will send back the theta. Theta is the actual cost of your subproblems, and lambda is the sensitivity. If we go back here, theta is this, which is the actual cost at the proposed point, and lambda is the cost. Sorry, the subgradient with respect to your right hand side. And so a synchronous way is that when you wait until everything is solved, and then you pass theta and lambda back to the reduced master problem, and then you perform the next iteration. So the plot down below also shows how these different processors work. So we have a master processor, which is the which coordinates everything and solve the reduced master problem. Once you solve the reduce the master problem in this part and propose an investment decision, you pass X down to different processors for different subproblems, and then you do this asynchronous parallelization, and then you once everything is finished, you pass back the theta and lambda. So this is how this like the scheme, the parallelization scheme we use in this study. Right. So another trick another thing that we need to do to improve Benders is the stabilization. In this case, we propose this centered point stabilization, which is that after you solve your reduce the master problem, you do not directly fix that point to your subproblems. Instead, you solve another stabilization problem, which is in this case is just feasibility problem, and that helps you to find a centered point. So instead, so in this way, it can avoid uh, well, it will help the algorithm to avoid going to some corner solutions where you will get very bad cuts. And in our case study, this center point stabilization is very helpful for solving large scale problems. So, well, for the sake of time, I cannot really go into much detail for this, but if you are interested in this, I recommend you to read the papers with different ways of stabilizing this Bender's decomposition. So now I would like to move to the energy system model we proposed in the paper. We call it the REORIENT model, and there are some novelties of this model. First is, of course, the uncertainty from operational and long-term time horizons, and also we integrate these different types of decisions, and we modeled a fairly comprehensive system, sorry, of the energy system. And as you can see, the components in the dashed oval are the new technologies you can add, including this offshore energy hub, and also the platform located battery for the oil and gas platform, um, offshore wind and solar farms, and you can also expand your onshore system or add electric boilers to your offshore oil and gas platform. And then you have different types of decisions. You can, expand your current system. You can retrofit the oil and gas platform to offshore energy hub, or you can also decide to abandon this oil and gas platform, or just decide to let it keep producing. Um, so this is the illustration of this integrated planning, and I will not present the detailed mathematical equations. Um, But here, let's move to the case study. We use the model and the proposed algorithm to solve this, integrated planning problem for the European energy system. And as you can see, we heavily focus. Well, we have very detailed modeling of the North Sea system, including all the oil and gas platforms in the Norwegian continental shelf, and also we have different types of pipelines, and that, well, we have a lot of candidate pipelines can be built for hydrogen, and also we include all the existing natural gas pipelines from the Norwegian continental shelf to the rest of Europe, to see whether under what condition under what condition it is economical to retrofit some of the pipelines. And also we have this power cables, which are represented by the black lines. Yes, so as you can see, we have uncertainty in all the time series parameters. That includes, the wind, solar, capacity factor, and hydropower generation profile, and demand, and all this, time scale stuff. And then we have different types of long-term uncertainty, which I will show you later. And it's a fairly complicated, complex system with many regions and technologies. Okay, so first, in terms of results, I would like to present the algorithm performance. So the first table summarizes the cases that we use to demonstrate to test the algorithm, and it's fairly large. It has up to 55 million continuous variables, several thousand binaries, and a couple, 100 something million constraints. And so the second table summarizes the different time spent using, distributed way of parallel computing or multi-threaded or a simple serial implementation. As you can see, the the two parallel computing case, in terms of time is significantly faster than the serial one, which is kind of expected. And but then what's interesting here is that if you see that, well, the distributed implementation means that we send the subproblems to different computers, like physically different. And then the multi-threaded is, you just send the subproblems to different threads on a single computer. And as you can see, the improvement from multi-threaded to distributed is not that significant in this case. Well, despite in case 4 is kind of more significant. And then we also tested, by increasing the number of workers, can we how this total time will change? And we notice that the performance does not scale linearly with as you increase the number of workers. So these are just some findings, but overall, this parallel implementation is quite efficient compared with a serial implementation. Uh, Okay, so now I present briefly some results related to the energy system decisions. Like I mentioned, we consider retrofitting the pipelines for hydrogen use, and we consider two cases. The first case is we assume the pipelines are not in use. That means there is no gas flowing in the pipelines because and this is not a very unrealistic assumption because there are some pipelines in the North Sea that are unused now. And in that case, we notice that, well, here I need to explain the cost here. So the cost means the how much it costs in percentage of building a new one. Because based on a report from Siemens Energy, retrofitting a natural gas pipeline for hydrogen, the cost is around 15% of building a new pipeline. Therefore, we did some sensitivity analysis around this cost, and then this pipeline 1 to 7 are the major pipelines that I showed in the previous slides, and as you can see, the star means the pipelines is retrofitted in all strategic nodes. So that means if the pipe, so basically the main message here is that if a pipeline is not used, then it's very economical to retrofit that for hydrogen because there is no loss in natural gas profit, right? And then okay, and then in the other case where the assumption is the pipelines are indeed used to transfer gas, and in that case, as you can see, the retrofit decisions the retrofitting decisions are taken in the very late stages. Basically the last 3, 4 stages you started to retrofit some pipelines, not all the pipelines. So basically that means if you retrofit an existing pipelines that are used for natural gas for something else, you really need to consider the loss of profit from natural gas. And then this is a plot summarizing the the system topology. Again, this is the expected system topology towards 2050 because as you know, we will have a trajectory like this for every a long-term scenario, but for the sake of presentation, we just presented the expected solution. And as you can see, by 2050, there are quite some not hydrogen pipelines, the green dashed lines, with significant capacity from offshore, from the North Sea to the rest of Europe. Okay, and well, these are just some detailed analysis regarding the connections of the lines and yeah. So I will not spend too much time on this. Um, but okay, so let's take a look at the technology, the mix of technology in Europe. Uh, well, this is very aggregated, meaning that we consider the entire Europe for wind, solar, electrolyzer, onshore, offshore, transmission line, and stuff. So what? Well, one thing I need to explain is that we did a comparison study, which is we compare the reorient model where we have different types of decisions with investment only model, which is let's say a more conventional planning model with only decisions in new capacities. And then by comparing these two tables, I would like to first focus on the electrolyzer offshore and onshore. Well, in both cases, as you can see, there is no electrolyzers until 2030, and this is mainly because the hydrogen demand is fulfilled by the SMR-CCS, the blue hydrogen. But then starting from 2035, as we decrease the CO2 emission limits, you have more you have electrolyzers to produce green hydrogen. And then what is consistent in both cases that it seems like the green hydrogen will be mainly produced offshore via offshore electrolyzers. That's quite interesting. And okay, so I think that's one of the main messages I want to send by looking at these two tables. Okay, so now let's go to the part of analyzing the uncertainty in energy system planning. So because like I said, a lot of several papers have been proposed to solve these type of problems very efficiently, but now we want to analyze how exactly this two-time scale uncertainty affects your investment, your system planning. So let's first take a look at the short-term uncertainty, and which again is this time series parameters. And then let's talk. Well, I will first present you the different ways of generating scenarios. One way is random sampling, which is you sample from historical data. Sample from historical data, and then you have 4 regular seasons. Spring, summer, the regular 4 seasons, and then you also have some peak season where the load is very high. And the second scenario generation routine we use is the moment matching. So the first step of moment matching SGR is the same as random sampling, which is basically randomly sample many candidate scenario trees, and then you choose some good candidate trees that can can match the some statistical properties of the original distribution. In our case, we checked the mean, the variance, and the skewness and the kurtosis and all this statistical moment. And so yeah, so basically it's one extra step from random sampling, and the goal is to have some more stable scenario generation. But well, I will show you in the next slide. The results is quite um, interesting and is not very is not what we expect. So well, so let's one way of how to say evaluate the scenario generation method is to test the stability and one we have well, usually you have in sample stability and out of sample stability, and what we find is quite interesting. Well, first of all, the two blue parts are the results from moment matching, and the green parts are the results from random sampling. And then what we find quite surprising is that as you can see, actually the moment matching is less stable, especially out of sample than random sampling. This is very, very surprising, but we observe this kind of behavior in some other studies as well. So I think it's more, some more, investigation is to be done along this line. Uh, and then we also take a look at the decision stability. So, well, first off, well, this plot gives you the objective stability, which is, the the objective function value. And then we also check the stability in your decisions. And of course, here we mainly looked into this. Um, some key renewable decisions. And as you can see, yeah, in terms of it varies quite a lot in both the random sampling and the moment matching, especially towards the future. And but if we take a look at the plot to the right, it's not hard to find that despite the so, a little bit unstable, but the structure and the mix of the wind and solar is quite similar, although the mean values are different across different, between moment matching and random sampling. And then we also take a look at this value of stochastic solution in terms of the short-term uncertainty. And and the good news is that we find the VSS is quite high, and that well across well using different scenario generation methods and different setup of the problem, and VSS is quite yeah, significant, and this illustrates the importance of including short-term uncertainty in your investment planning problem. So now let's move to long-term uncertainty. So here we consider, I think in total 8 different long-term uncertain parameters. 3 of them are the right-hand side, the CO2 limits, power demand scaling, hydrogen demand scaling, and also 5 of them are, the cost coefficients, the gas prices, the technology costs, mainly around the renewable technology costs and CCS. So here the scenario trees are generated. Well, the mean tree, the tree with mean value is from some expert opinion, and then we generate the branches based on that. Okay, so let's take a very quick look at the results. So first of all, this plot gives shows you the difference between the deterministic case and the stochastic case, and the different cases in the horizontal axis are different uncertain parameters. So in this case, we only consider one uncertain parameter at a time. So these are uh, uh, different. Okay, so these are 6 different cases, And as you can see, um, in terms of renewable, this is the investment difference in, let's say, the green bar here, the renewable generators. As you can see, compared with the deterministic case, you in the stochastic case in 2040, well, first of all, you have a earlier investment in um, in renewable, and also more investment in renewables compared with deterministic case. And also you kind of have less investment in fossil uh, compared with the deterministic. Well, I think there is quite some interesting there are quite some interesting insights we can get from this, and but I think I'm a bit I need to be a bit faster now. So we also take a look at the hydrogen production, the difference in hydrogen production capacity, comparing the stochastic cases with the deterministic case. And as you can see, um, um, uh, well, I want to highlight one thing, which is, when the CO2 cap is uncertain, we really have a lot less hydrogen production capacity from SMRCCS, because especially towards 2045, because you have very strict CO2 emission limits, and SMRCCS is not completely emission free. Although you have some electrolyzer compensate for this reduction in the capacity in SMR-CCS, but it's not, it's really not fully, how to say, fully compensated for the reduction in SMR-CCS. So as you can see, well, basically what I want to illustrate in these two plots, this one is that when you consider uncertainty in long-term, when you consider long-term uncertainty, you have really different. It can affect your investment decisions quite a lot. So um, and here is just another study. We combine two long-term uncertainty and check it with treating them separately. So basically, you have CO2 cap as uncertain, demand scaling as uncertain, and then the third case is where we put these two uncertainty in the same scenario tree. And I think the main message here is that it doesn't change the mix that much. You still have compared with the deterministic case, uh, there is difference, but not that significant. Um, Okay, so I also present some results regarding the uh, value of stochastic solution in terms of the long-term uncertainty. And for that, we did the traditional VSS calculation, and we also take this rolling horizon value of the stochastic solution, which is proposed by a paper from I believe Francesca Maggioni. And so basically, rolling horizon value of stochastic solution is you start with the whole tree, and whole tree with you only solve the mean tree, the tree with mean value. So basically a deterministic problem, and then you can get the first two stages decisions, and then for the next stages you again treat them as deterministic, which is you just replace the tree with its mean value, and then you solve again, you get the next stage decisions, and then do it so on and so forth. So this is, let's say, this is less naive than purely deterministic. And then when compare the rolling horizon VSS and the traditional VSS is quite significant, which is 29.7%. And then in terms of rolling horizon VSS, it's only 1.7%. So the message here is that um, yes, MHS multi-horizon stochastic programming compared with deterministic is of for sure has a lot of value in terms of long-term uncertainty modeling. But if you can do rolling horizon, it can also capture quite well uh, the uncertainty. Well, I think let's say let me rephrase it. I think is more like rolling horizon is a less naive way of than the deterministic counterpart. So in summary, we propose this stabilized parallel bundles decomposition, which is quite fast, and then we analyze the multi-timescale uncertainty. We test the different scenario generation routines, and we have some observations in terms of the stability and the VSS of both short-term and long-term uncertainty is quite large, which suggests it's really important to consider multi-timescale uncertainty when you do your system analysis and system planning, and yes, and some other the messages I told you in when I described the results. So here is you can scan this code to take a look at the all the publications related to the algorithms we developed and of course the papers I used in this talk. I think I omit a lot of details, so it's good to check that those. And before I finish, one last thing is this advertisement related to a special issue that we just propose, which is this interfaces between AI and decision making under uncertainty on computational management science. So if you have any work, either theoretical or application that integrates AI and decision making under uncertainty, please consider submit your work to this special issue. So that's everything, and here are some references I used in this talk. Thank you.